Hello friends, let's try a very interesting problem from set theory, number of relations defined on two sets. In this video, we will talk about not only total number of relations but also different types of relations like reflexive, symmetric, anti-symmetric, transitive and equivalence relations. Let's dive into each of them one by one. Let set A has n elements, then the Cartesian product set A cross A is the set of all ordered pairs. This means, we're pairing every element of A with every other element of A, including itself. So how many ordered pairs will we get? It's n square. Now how do we define relations? It's just a subset of a cross. So number of relations will be 2 raised to the power n square. Let's understand reflexive relations on a set with a clear visual approach. Suppose set A has n elements. Then the Cartesian product across A has n square ordered pairs. Now, let's organize all these pairs in a matrix form. So, every cell, I, j, in the matrix represents the pair, AI, AJ. Now, what is a reflexive relation? A relation R on set A is reflexive if it includes all the diagonal pairs, A, A. For every A in set A, so, we must include all n diagonal elements in any reflexive relation. These are fixed. They have to be in the relation. Now, what about the remaining entries? Well, there are n square minus n non-diagonal pairs in the matrix. And for each of these, we have two choices. Either include it in the relation, or leave it out. So for each of these n square minus n entries, we have two options. By the multiplication principle, the total number of reflexive relations is 2 raised to the power n square minus n. Now let's talk about symmetric relations on a set A. What is a symmetric relation? A relation R is symmetric if, whenever A, B, in R, then B, A, must also be in R. Let's break the matrix into two parts. First, diagonal elements, pairs of the form, A, A. There are exactly n of these. Each diagonal element can be either included or not. So, we have two choices for each diagonal elements. That gives us, number of choices for diagonal elements is equal to 2 raised to the power n. Second, off-diagonal elements. Now, here's the key point. To maintain symmetry, both AI, AJ, and AJ, AI, must be included together, or both left out. So we treat each such pair as a unit. How many such unordered pairs are there? From n elements, the number of unordered distinct pairs is nc2. And for each of these, again we have two choices. Include both AI, AJ, and AJ, AI, or exclude both. So the number of choices for off-diagonal entries is 2 raised to the power nc2. Final calculation. Total number of symmetric relations is 2 raised to the power n into 2 raised to the power nc2, which simplifies to 2 raised to the power n square plus n by 2. Let's talk about anti-symmetric relations, and how to count them. First of all, what is an anti-symmetric relation? A relation is anti-symmetric if both AI, AJ and AJ, AI are in the relations, then I must be equal to J, so for I not equal to J, both cannot exist together in the relation. Now let's find total number of such relations. For diagonal elements there is no constraint, so number of choices are 2 raised to power n. For off-diagonal elements, consider unordered pairs like AI, AJ and AJ, AI. For each such pair, we consider the 4 possibilities. Include AI, AJ, only. Include AJ, AI, only. Include neither. Include both, but we cannot include both, because that would violate anti-symmetry. So eliminate the 4th choice where both are included. So for each unordered pair, we have 3 valid choices. Total choices for off-diagonal elements are 3 raised to power n square minus n by 2. Let's talk about transitive relations, and why they're so mysterious when it comes to counting. A relation R on a set A is transitive if, whenever A, B, in R and B, C, in R, then A, C, must also be in R. Sounds simple? But here's the catch. To check whether a relation is transitive, we look at all possible combinations. But to count all such transitive relations, we can't use a simple formula. There is no closed formula for the number of transitive relations on a set with n elements. Researchers have studied it using combinatorics, graph theory, and even matrices, but the numbers grow unpredictably. For small n, the counts are known. N equals 1 to 1 transitive relation. N equals 2 to 5 relations. n equals 329 relations, n equals 4 to 355 relations, n equals 5 to 6942 relations, and beyond that, it explodes. So yes, there are research papers and recursive algorithms, but no clean shortcut like we have for reflexive or symmetric relations. Now comes the last, but definitely not the least. Let's talk about equivalence relations on a finite set. So what is an equivalence relation? A relation R on a set A is called an equivalence relation if it satisfies three properties: reflexive, symmetric, and transitive. These three together form the foundation of how we classify and group elements. And here's the cool part. Every equivalence relation on a set corresponds to a partition of that set. That means, the number of equivalence relations on a set of size n is equal to the number of ways we can partition the set into non-empty, disjoint subsets. The total number of ways to do this is called the Bell number, denoted by Bn, which is given by this recursive formula as Bn plus 1 equals to summation k equal to 0 to n. nck, bk. Here are the first few Bell numbers. B0 equals 1. B1 equals 1. B2 equals 2. For higher value of n, we use recursive formula. Now let's find B3, which is equals to summation k equals to 0 to 2 to 2ck, bk. Now expand the summation and substitute all the values. We get B3 equals to 5. For higher Bell numbers follow the same process. And that brings us to the end of our journey through the world of relations. From understanding the basic idea of a relation, to exploring reflexive, symmetric, anti-symmetric, transitive, and finally the powerful equivalence relations, we've covered them all, step by step. Along the way, we discovered how to count these relations, how they connect to real mathematics, and how beautifully concepts like Bell numbers tie everything together. Whether you're preparing for Olympiads, or just building a strong foundation, this knowledge will give you an edge. And remember, math is not just about solving problems. It's about seeing the patterns, the logic, and the connections that make it all click. If you found this helpful, don't forget to like the video, share it with your friends, and subscribe to JE Maths Unlocked for more high-quality, no-fluff explanations. This is your host, signing off. Until next time, stay curious, stay sharp, and stay ahead.